I want to talk about a brief history of the Internet. Now, this is a topic that takes weeks to do properly, and only a fool would try to do it in less than an hour. Then I want to talk about the early vision, then the future vision, and ordinarily the presentation would end there. But I'm going to continue, time allowing, and I want to express a concern about what we've done and what we're heading into, and it may or may not be what you anticipate, so we'll leave that to the end. And then finally, I want to make a complaint. I want to complain to members of this audience and others in the field who do performance evaluation. I've been around long enough, so I'll claim I have the right to make this complaint, and hopefully it'll be taken in the right way. So, introduction. I have an ophthalmologist. His name is Larry Garwood. And his father asked him, what is the Internet? It's a fair question. And Larry came up with a great answer. He said, the Internet is everything. Past, present, and future. A little bit ambitious, but not totally wrong. Then his father responded and said, look, during World War II, I was in the Canadian Navy. And I was assigned to a landing craft. I commanded one. And we were involved in something called Operation Dragoon. Anybody remember what Operation Dragoon was? Anybody remember Normandy? Well, Dragoon was the second assault on Europe from the southern France. And he was involved with that. And he said to Larry, if you're such a smart guy, you go find that landing craft on your net that has everything. So Larry looked around and he went to finally, after a long time, went to the Canadian Maritime Museum website, and he found the following. He found a picture of his father's ship. It had just rounded Gibraltar. This ship then hit a sea mine, blew a hole in the hull. They went to the port of Polos in Greece for repair, and the sailors got bored. So in their great bravado, they got in their landing craft, unarmed, to visit the port of Athens at Piraeus. Well, the Germans were still occupying Piraeus at this point. And the Germans knew that Dragoon was going to occur. So these idiots, unarmed, come over the horizon. The Germans see these landing craft coming. They panic. They blow up the stockade, and they evacuate. Lucky for these guys. The population comes out and says, you have liberated us. Everybody's happy. Next picture is this one. If you look carefully, there's his father's landing craft. And there's his father. That's the Internet. It's got it all. Just go out and find it. I think that's a perfect example of what the Internet can do for you. So let's talk about this thing called the Internet. I sound like I'm in a barrel. Does it sound like that to you as well? No? Okay. What makes the Internet tick? Two things. The people, they generate things, and the culture, which allows those generated things to be shared freely and liberally. And most of all, the Internet creates communities. People who have a common interest can find each other and do something about it. It's changed a lot. It's removed a large number of barriers. It's removed, for example, the barrier of distance. How far you can reach. How many people you can interact with. The speed with which you can interact with them. Increased anonymity, a good and a bad thing. Reduced the cost of communicating. Expanded how much you can reach. So these are very interesting barriers to be breaking down. We haven't yet beat the speed of light, but we're on our way. So, what other barriers are removed? Well, for interaction, political interactions are easier. Economic, social, cultural, racial. Physical handicaps are less important. Physical appearance doesn't matter anymore. There's this wonderful cartoon from the New Yorker. It's got a picture of a big dog talking to a little dog. And the big dog says to the little dog, on the internet, nobody knows you're a dog. Well, this is true. And it's really a kind of leveling, or you can hide and do bad things and nobody knows you're a bad dog. But that's the kind of thing it's done. What else is done? It's create communities, okay? It provides access to a lot of knowledge, amplifies the things you can do, facilitates accountability if it's done right. Speed of light across the globe. Event occurs, you know about it within seconds. Has some political implications. It also raises doubt about what it is you're getting and who it is that's giving it to you. So these are some of the consequences. But it's basically changed all of our institutions, our business practices, behavior, attitudes, social interactions, educational process, political processes, and our work and entertainment habits. So this is a pretty interesting thing that we've created over these many years. Let's talk about this history. Where did it all come from? And maybe we can talk about where it's going. So let's see. 1969 was a really great year. A lot of important things happened. Put a man on the moon. Woodstock Festival of Massachusetts. People dressed up in funny costumes and did funny things. An event with probability 0 occurred. It happened again last year with the Red Sox. Charles Manson murdered some people in California. Oh, and by the way, the internet was born. At that time, everybody recognized these events. Nobody recognized the internet was born. Nobody noticed. It happened. What was that? Before the beginning, before '69, the groundwork was being laid. It all began in 1957. Sputnik was launched. Caught the United States with its pants down. President Eisenhower said, that'll never happen again. He created the Advanced Research Projects Agency as a response to support advanced technology, which they did. At around the same time, there was this person at MIT doing some mathematical theory of packet networks. That's what it looked like then. This is what it looks like now. Paul Barron, shortly thereafter, at RAND, was proposing to break messages into segments and send them across the network, reassemble them. That's what Paul looked like before and after. Licklider, a giant of a man in those days, basically had a vision of a galactic network. He was the first head of the computer portion of ARPA, the Information Processing Techniques Office. He gave his vision of a galactic network. He had no idea how to make this network. Little did he realize that I had already laid out the design technology and the methodology for doing this. Neither did I have any idea that he had done that. And we were both at MIT at the same time. Shows to you what communication means. At any rate, the groundwork was laid. All this came out, all this wonderful stuff. Nobody cared. Again. AT&T said it wouldn't work. And they said, even if it does work, we want nothing to do with it. And we know the story of AT&T. So, in '65, mid-'60s, other things began to happen. Doug Engelbart invented the mouse, but he also began to think about hypertext, perhaps an even more important concept. In '65, Larry Roberts, pictured there before and after, and Tom Merrill ran an experiment to connect MIT Lincoln Labs with SDC across the country on a dial-up connection. It was a very difficult thing to do. It was ugly, awkward, cumbersome, did not work well, but they made it happen. And they wrote a paper in 1966 about that. 1965, Donald Davies coins the word packet. We knew nothing about that word until that time. In 1966, Bob Taylor, shown here, recognized that ARPA, who had been funding research all this time, had a need for a network. So suddenly, I realized these ideas we had laid down may actually get implemented. It's only a dream at this point. And he brought Larry Roberts to Washington to actually manage this project and set together the full architecture. In '67, Donald Davies created a one-node National Physical Laboratory net. Now, one node does not make a net. The UK, in its infinite wisdom, chose not to fund a multiple node network. If they had, the person speaking to you today would have a British accent. But they chose not to do it. 67, Wes Clark came up with a great idea. He said, look, if you're going to do this thing called packet switching, don't overload the host with all the operations. Offload it onto a separate processor, a switch. A switch became a packet switch. So this is a great idea. He was working at Lincoln Lab at the time. In 67, by 67, many researchers have been supported for years under the ARPA program. And each one of them had developed their own specialized capability. At Utah, there was graphics. At UCA, simulation. At SRI, database. At Illinois, high performance. So every time ARPA came to a researcher and said, would you please do research for me? We'd like to fund you. You have some good ideas. Researcher response was, oh, you want me to do research? Fine, I'd be happy to do it. Buy me a big computer. ARPA said, fine, we'll do that. But not only that, I want the power that everybody else has. I want the graphics, I want the simulation, I want the database, I want the high performance. And ARPA said, we can't afford to do all of that. And if we're going to fund you, we're going to make an offer you can't refuse. And the offer that you couldn't refuse was, you're going to join a network. You want to do graphics, you log on to Utah. You want to do high performance computing, you log on to Illinois. And so the concept was born that there would be a network. The reason was to do resource sharing, and off we went. So in 1967, a bunch of us got together to specify what this would look like. As a result of that, Larry published an ARPANET plan. The request for proposal went out in late 68. And toward the end of 68, Bolt, Baranek, and Newman, a Cambridge, Massachusetts firm, won the award. It was their job to select a switch. The switch was going to be called an Interface Message Processor, IMP, IMP. Frank Hart was in charge of it. Bob Kahn was one of the system designers, suggesting what the architecture would be. In 1968, my lab at UCLA was selected to be the first node on the network because we knew about the technology, also to become the network measurement center because we knew how to break the network. It was our job to stress the network and find ways it would not work. The switch was supposed to arrive in September of 69, less than 9 months from the time they had that award, less time than it takes to make a human baby. In that period, both BB and UCLA were real busy getting ready. They making the switch, we making the interface. And they delivered on time. They delivered on time. Just before they delivered, UCLA put out a press release. Here's the first page of that press release. It was put out in July of 69, 2 months before the net came up. And in that, I talk about what the applications might be, what the network might look like. And on the second page, a 2-page press release, the final paragraph says the following. As of now, computer networks are still in their infancy, but as they grow up and become more sophisticated, we will probably see the spread of computer utilities, which, like present electric and telephone utilities, will serve individual homes and offices across the country. This is 2 months before the net even came alive. So if you look at what that 69 vision is, I'm going to return to it later. There were a few components. First component is the concept of web-based services being anticipated in that you could suck power out of computer utilities out there in the net. The idea of an invisible, always-on access, just like electricity and telephony. It's there, it's invisible, it works, you don't think about it. And third, you'd be ubiquitous. From your homes, your offices, anywhere you can connect to this thing. So continuing now, on August 29th, BBN delivers the first switch. That was a Labor Day weekend. On September 2nd, the first day to move back and forth between the switch, this IMP, and the UCLA host running a local time-sharing system. This was the first time, the first piece of the Internet equipment began to talk to the outside world. This is when, if you will, the infant Internet took its first breath of life. The IMP looks like that. A closer picture of the panel looks like that. It was a wonderful old machine, but advanced at the time. That's what it looks like inside. That is so ugly, it's beautiful. And you have to love a machine like that. We decided to keep a log of what was going on. You can tell this is an engineer's log. And there's a major entry in that log, on about the 5th page, dated October 29th, 1969. At 10:30 in the evening, we made an entry which said that we talked, host to host, from UCLA to SRI. This is a record of the very first message on the Internet. The idea was to connect from our host machine through the first switch, through the first backbone link in the network, through the second switch to the end host. So, What was that first message? Was it a good, juicy one, like Morse had, what had God wrought? Or Alexander Graham Bell, pretty smart guy, Watson, come here, I need you. Or Armstrong, giant leap for mankind. Those guys knew what they were doing. They had a good message, they understood PR, they got the media there, there were records made, and we all know what they said. 150 years later. So what was the big internet going to say? Well, we didn't care. All we wanted to do was log in. I mean, that's all. Just wanted to log in from our host to that host. To log in, you have to type LOG, and the SRI host knows what you're trying to do, so it does a command completion and types the IN field. That was the job. In order to make sure it worked, we got a telephone connection between Charlie Klein, our program at UCLA, and his compatriot at the other end. And so we proceeded. The big experiment. By the way, how many people were there? 2. Him and me. No camera, no tape recording. The only record was what I showed you already, an entry in the log, a one-liner. So Charlie typed the L, and he said, did you get the L? And the answer was, got the L. Okay. Sent the O. Did you get the O? Got the O. Sent the G. You get the G? Crash. System went down. Now, what went down? This is very important. It wasn't the UCLA host. It wasn't the UCLA switch. It wasn't the backbone link. It wasn't the SRIM. It was the SRI host. It was their responsibility. They said it had a memory leak and it went out. So what was the first message ever on the internet? It could not have been more prophetic. Lo and behold. Couldn't have planned it better. That's probably the most important message ever sent in the history of mankind. So, continue to grow. We had the first message in October, 69. Also in 69, we brought in Howie Frank at Network Analysis Corporation to help do topology design. Steve Crocker at UCLA released the first request for comments, which described the host-host protocol, set up the network working group. In 1970, we spanned the country. UCLA to BB&N, first link, already in that first summer. Also in 70, we released the first network protocol, the Network Control Protocol, NCP. 71, BBN said, we're going to develop a machine and launch it, which allows you to connect to the network without going through a host. You can connect right into an IMP, a terminal IMP, called a TIP. Good. 72, Ray Tomlinson puts email on the network. It was already on time-shared systems. He added it, and boom, all the traffic on the network suddenly was email. It happened almost overnight. That's the first time I realized that this was not about computers talking to each other, but it's about people communicating, and that's still the case today. 72 is a public demonstration. 72 also, we connected in another network to the ARPANET, basically the packet radio Aloha Net. That's Norm then and now. He still surfs. 73, we deployed a third network, the SAT network. First international connection, satellite across the Atlantic. In 73, Vince Cerf and Bob Kahn essentially designed TCP and announced it at a meeting in England. Bob Metcalf develops Ethernet idea at the same time. 75, the ARPANET management transfers to the Defense Communications Agency. UCLA had been managing and running experiments, stressing the network, finding failures all this time. DCA took it over, never made another measurement. Now it's very hard to take the network down because you're not allowed to if you're doing things right. In 78, TCP was split into TCP IP under the influence of Danny Cohn, Dave Reed, and John Schock, whose picture's not here. They said, look, TCP will not support real-time traffic, allow us to run UDP over IP, and that's one of the reasons we have streaming traffic today. 1980, these four, Larry Landweber, Dave Farber, Tony Hearn, and Peter Denning, got together. They proposed a thing called Computer Science Network, allowing people who were not funded by ARPA to get onto the ARPANET. Very important step. PC appears in 1981, IBM's PC. Notice NET was around for a long time by then. Nobody had heard of PCs until around this time. It was easy to adapt a PC to the NET. The architecture was flexible enough to allow devices like that to come in. 83, basically the ARPANET said, you must run TCP IP if you're going to be part of the ARPANET. '83, the MilNet is split off from the ARPANET. '84, domain name system is introduced by Paul and John. In '86, NSF, who was supporting supercomputer research in centers across the country, decided to use the backbone part of the Internet, which was now going to be taken over as NSFNet at a very slow speed. Steve Wolf was in charge of the effort. And so suddenly more than computer scientists were allowed in. Physicists, chemists, physiologists, meteorologists, archaeologists, biologists were all let into this network, and it greatly expanded the constituency and the kinds of traffic and the kinds of locations that were now part of the ARPANET, the Internet at that point. In '88, they upgraded to T1 speeds. 1988, the first bad thing begins to happen. Robert Morris unleashes the first Internet worm. Okay? We noticed it. We said, that's sort of interesting. In '89, we celebrated the 20th anniversary. The network was already 20 years old by this time. 1990, the ARPANET is replaced by NSFNet. That's now running the backbone. '91, World Wide Web comes available from Tim Berners-Lee. The concept, anyway. 1991, NSF opens up the Internet, basically, to commercial use with a very relaxed, acceptable use policy. We begin to see the dot-coms coming in at this point. They saw the power of email in particular, so they began to join. In '92, the Internet Society was formed. '92, NSF goes up to 45 megabits per second, making it a serious network now. '93, Mosaic browser comes out of University of Illinois with Mark Andreessen. '94, Cantor and Siegel introduce spam. Something else is happening now. Okay, these two people were the most hated individuals on the Internet that day. They sent an email around, which was an advertisement on our Internet. Here's a picture of the first email, first spam ever. April 12th, 1994. And they're telling people they're trying to sell their services as lawyers to help people get green cards. Deadline's coming, we're going to help you do it. We looked at that. They sent it across the network. We said, how dare you do that? No, you can't do it. Bad. Stop. We sent so much mail back to them, we took their server down. So one of the unintended consequences of this first spam was to create the first denial of service attack. And so it's been continuing, as you know. '94, BBN celebrates the 25th anniversary. '95, the dot-com boom begins. Everybody thinks there's a new economy. Profit doesn't matter. Eyeballs do. '96, deregulation of data networks. '96, more email than postal mail in the USA. This is a significant change. Internet 2 Consortium is formed in '97. Wi-Fi standard comes out in '97. Only 9 years ago. Hard to believe. '97, Barry Leonard and a bunch of the rest of us published a rather interesting paper about the Internet and its history. It's worthwhile reading. Blogs begin to appear in '98. Voice over IP begins to appear. UCLA celebrates the 30th anniversary, 1999. Napster rolls out in '99. Dot-com bubbles bursts in the year 2000. Napster goes out of business. Year 2001. Forced out of business. Services suspended. Flash mobs gain popularity, 2003. World Summit Information Society takes place. First meeting in Geneva. UCLA celebrates the 35th anniversary. Time is moving along. 2004, mobile phone revenue begins to exceed fixed line revenue in the United States, each a $50 billion industry. 2004, USA leads the world in the length of a cell call. Interesting statistic. Why? It had to do with the charging plan. We introduced flat service so people could stay on the phone all they wanted. So you were not limited by the cost, but limited by how long you wanted to talk. 2004, camera-enabled phones are outselling, with the cameras in them, are outselling digital cameras and film cameras. So there's a certain move toward convergence occurring at this point. 2005, 4 times as many cell phones sold as laptops. 2005, Google is coming on really strong, the darling of the Internet. Invest, invest. 2005, peer-to-peer grows. Supreme Court decision supports the Recording Institute of America. Grokster closes down. 2005. 2005, second meeting takes place for WSIS. in Tunis. Basically, they create this Internet governance forum, which allows the stakeholders to discuss their issues and be heard. Next meeting will take place later this year in Athens. 2005, ATT disappears. 1983 was the largest corporation in the world. November 18th, it ceased to exist in 2005. SBC bought it. It employed some of the world's best scientists, worst managers, and died of a disease. A very serious disease. But not to worry, it's been reincarnated. SBC renames itself as AT&T. So, now I hear a bit of a nervous laugh from some of you out there because a lot of you were involved with that cycle of unfortunate circumstances. So let's review a little bit what I just said about the history. Here's some of the early pioneers, people who sort of started the ideas. Here are the people who were there at the early days of the implementation. Here are the value adders who helped produce it. Here are the people who helped launch some of the major services. And finally we come to the billionaires. Okay. And they were Johnny-come-lately, but they had an impact for themselves. So what was the early vision that I had then? Well, I already showed it to you. It was in that press release. I want to say more about that and try to extend it. The press always comes to me, and they ask me, did you see this coming, this enormous rise of the Internet? I had 3 interviews yesterday. They all asked that question. Now, typically when they ask that question, most people will say, oh yes, I saw it all coming. Here's exactly what was going to happen. I predicted it all. When they ask me, my answer is, well, it's yes and no. The yes part was in that press release. The no part, among other things, is that I never predicted that my 98-year-old mother would be on the Internet today, and she is. I missed the people part, as I said earlier. When email came in 72, it began to dawn on me this was about people and not about machines. Anyway, what was that early vision? I'm going to restate it as 5 salient points. First point is Internet technology will be everywhere, always accessible, always on. Anybody can plug in any device anywhere at any time, and it will be invisible, like electricity. Shouldn't have to worry about it. Well, the Internet almost got it right. Here we are, 37 years later. What did it get right? Well, is the Internet everywhere? Yep, got that part right. So it was accessible? Yep, pretty much. Always on? Yep. Anybody plug in any device anywhere at any time, easily? Not quite. We're working on that. It's now in the hands of the industry as opposed to in the hands of the visionaries. It's happening. We'll talk more about it later, but that's moving along. It's not quite there. Is it invisible? No way. If you think booting up Windows is invisible, or connecting your latest cell phone to the latest networking technology, good luck. If you can even operate your VCR or use all the features of Microsoft Word, it would be invisible, but you can't. It's just too hard. Still, the human interface is just terrible. So what did the Internet get wrong? Internet, in those days, when these protocols were being developed, took this model of a user, namely a desk-bound mentality, you and your machine with the table. It said basically that you, the user, your device, your IP address, and your location were all tightly coupled. That's you, your machine, your IP address, and your location. It's no longer the case. You now lift up that machine, maybe a laptop, maybe a smart PDA, and you walk out into the world, and you leave behind a lot of that stuff. Your IP address may change, your device may change, your location may change, and who you are, your identity may change. So that model is busted. And that's part of the reason that some of those achievements, those visions, have not yet been realized. So let's look at some of the enablers of the Internet. What are the characteristics? It allows anybody to reach hundreds of millions, billions of users. It's a good thing. Easily, quickly, at no cost in time, money, effort, and anonymously. That's a pretty good system. Lots of good things can happen. Unfortunately, that's also a formula for creating the dark side of the Internet. If it's too easy, and you can be too hidden, and it costs you nothing, They want to do some bad things if that's the way your mind works. And there are enough people out there doing bad things. So the flexibility of the early internet, which allowed it to grow, and there's very little I would change about the way it was set up, this open access, trust in each other, freedom of access, sharing ideas, allowed the network to grow to where it is today. The one thing we probably should have put in that we didn't was at least some strong user authentication. We could have done that. We didn't. And now it's a patch, and the security issues and the privacy issues become much more serious. But there's the dark side. And if you wonder about things in the dark side, here's an example. What if your screen suddenly popped that baby up on you? And I don't like the choices it gives me. This is due to Bill Cheswick. It's a wonderful idea. So the future vision, let's talk about it. Well, in infocom2006, I had a vision of the future. It had three components. Three components were basically three phases. Advanced network technology, well, that's always going on. That pretty much takes care of itself. You're not going to stop the progress of technology. So I'm going to wipe that off my slate. Let's move it along. Nomadic computing, the idea of being able to connect in any device, any location, any time. And smart spaces, bringing cyberspace out from behind the screen of your machine into your physical world. That was then. Here we are today. Let's extend the vision. Still nomadic computing hasn't quite happened yet. I still put that on the list. And also smart spaces is not yet there. It's a long ways from being there. And we'll talk about each of these in a moment. Some additional things, though. Ubiquitous computing. We want this everywhere we go. We'll talk about that. Convergence of a variety of things I'm going to talk about, and finally some software agents out in the net. So let's talk about the first, nomadic computing. And I discussed this idea when I was here 6 years ago. In your office, you have three wonderful capabilities. First of all, you have a high-performance workstation. Secondly, you've got high-speed networking. And third, you've got a network administrator to make it all work for you. They load your software, load your hardware, set up the network, reconfigure your machine. And probably everybody in this room doesn't need the services of this administrator. But most of the rest of the world does. That's a very important function, to keep the system alive. When you lift up that laptop and leave your office, as I said before, you leave the last two behind. You leave your networking behind, and you leave your administrator behind. Now, when you go someplace else, you're more than likely to find networking. It's here in this room right now. It's in your hotel room. It's in the airplanes, in the airports, etc. So number two is not so bad, but number three is still an issue. When you get there, you're an alien in a new environment. And it's not that easy to connect your device into the network. If you're sitting behind a proxy in your home office, your laptop's going to be looking for a proxy or ARPing for its own router. And something has to be done. There's technology that can do that. I'm sure Charlie's going to talk some about some of these ideas when he makes his presentation, but it's still an issue. What you really want is a kind of portable network administrator to come along with you or be in the system somewhere when you arrive. And that's the concept of nomadic computing. To summarize it, to provide the system support so you see the same set of services and capabilities no matter where you are, no matter what you have, and no matter when you get there. That's moving along. As I say, the industry is rolling out products here. Embedded technology. Our environment will be alive with technology all around us. This room should know I'm here, should know every one of you is here, should provide to you the same set of privileges, profiles, and preferences that you have back in your home office. You should be able to talk to this room. You should be able to respond with a hologram, with speech, etc. It'll be everywhere, in the walls, in the desk, in the belt, in my client glasses, in my refrigerator, in my automobile, my fingernails, in my hotel room. And what's this going to be? It's going to be all the obvious things: logic, memory, communications, actuator sensors, cameras, microphones, speakers, displays, and more. Every kind of embedded technology. So the idea of embedded technology, smart spaces, is intelligent devices embedded in the physical world, taking cyberspace out from behind the screen and embedding it where you live. What's going to be connected? Well, if you look at some recent chip deployments to get an idea what's being connected, this is a couple of years old, but you get the idea. There are about 150 million logic processors out there, the things that run your laptops and your computers, twice that number of embedded microprocessors, twice that number of DSPs, and more than 10 times that number of microcontrollers, we've now exceeded by far the population of the world, and that's per year. So those are the things that are being deployed out in the internet. So where are I? Well, they're on my wrist, the device I carry around with me, they're whatever the heck those things are. Intelligent home. It's the people who like to carry it all in their waist. They seem to enjoy it, and they've got all kinds of goodies. And then they'll come at you with their head-mounted displays, look very geeky. And I know those geeks, and they are geeky. It'll soon be in your eyeglasses, and you won't be able to notice it, but you'll be able to read a little display, direct retina feed, while you're walking around, if you want to do that. So, that's the idea of smart spaces and smart nets. Is it going to be everywhere? You're going to gain access everywhere? Well, let's look at the sequence of ubiquitous technologies. The first and perhaps the most important was dial-up. Dial-up was terrific. It was everywhere. It was low speed, but wherever you went, you could find a telephone dial-up. Fine. Then we see the broadband access, copper, cable, satellite, cellular now, 4G, 3G, 4G, gaining access. Almost everybody in this room probably has a device that can read the web right now from their belt. That's good. Wi-Fi, WiMAX, fiber, etc. These technologies are making the communications access ubiquitous. It's happening. It's moving along. It's taking care of itself. Wherever you go, you should be able to get on the internet. Fine. Now, convergence. This is a newer observation. We're seeing convergence of content, of function, and services all into a single device. A lot of disruptive forces making this happen. Everything's being digitized, broadband's happening, and devices are getting smarter, smaller, cheaper, faster. It's all happening in the palm of your hand. So let's look at the mobile device, where this convergence is taking place. It could be that, it could be that, it could be this. It could be that. Not only music files, we're watching TV on these things right now. There's not too much you can't do with these services and convergence on single devices. This has become a content rendering device instead of a cell phone. Its job is to take whatever stream it receives and render it so you can see it. Now, on the road, as I mentioned last time, I carry a lot of garbage with me. Digital watch, two-way email pages, not all with me today, by the way. Cell phone, MP3 player, PDA, camera, GPS, notebook, computer. If I'm doing that, what am I carrying? I'm carrying 8 displays, 6 keyboards, 5 speakers, 3 microphones, 8 clocks, 8 batteries, 7 chargers. That's the worst of it, by the way. And 4 communication devices. This is nuts. Shouldn't have to do that. And in fact, the convergence story is making that go away. So, for example, what am I carrying around again? It could be a phone, it could be a pager, it could be PDA, an FM radio. I'm adding some things now. A television, Rolodex, PC, walkie-talkie, camera, game console, camcorder, GPS device, a watch, a portable video system. Let's converge it all into one device. Let's put it in that device. There it goes. That was hard. Okay. So it's in there now. It's going to do it all for me. Okay? These are the devices that are coming along with that kind of convergence. We've seen function converge just now. This thing that was earlier formerly known as a cell phone will now be called a communicating multifunction rendering device. Each of those adjectives is very important. It needs all that functionality, and that's what it's becoming. Here's a converged phone. Those keyboards are getting smaller. My fingers are not. Those screens are getting smaller. My eyes are getting worse, not better. So the human interface, again, becomes a problem. In fact, if we look how far we've come in 35 years, back in '69 when the Internet was started, we had an IMP, a mini-computer packet switch. And what speed did it communicate to the Internet with? Well, 50 kilobits per second. Blazing speed at that time. 35 years later, Trio comes out. What speed does it connect to? 50 kilobits per second. How far have we come? Well, that's going to change, but there's a kind of irony in this. 35 years of progress. Is there a mismatch here, by the way? Let's think a little further. Take that device, put it in the hands of a teenager. Tell a teenager, go ahead and use it. Now, that teenager is going to have access to the Internet, and through the Internet, access to a server farm. Now, the one thing you do not want to do is interrupt a major operating system like that server farm every time she hits a key. Namely, you don't want to nickel and dime that server to death. The other thing you don't want to do is turn a direct memory channel from that farm directly onto her, because she's not going to be able to take that. And in fact, that won't happen. What's going to happen is the Internet's going to eat up all that data and trickle it out of whatever speech is connected to. And the Internet is a very expensive storage medium. The point here is there's something to be thought about here. This has to do with flow control, congestion control, management from end to end. There's some good research that can help analyze, model this, and hopefully alleviate that problem. So what is the mobile device? Well, it depends who you ask. Traditional view is it's a phone. Hollywood says, it's a tiny TV. Silicon says, no, it's a PDA. Game industry says, well, it's a Game Boy. What's the right answer? It's something new. It's a new medium, new applications, new ideas. Think big. It's a fourth screen now. The movie screen participated with the TV screen, participated with the PC screen, now with the cell phone screen. They're all competing with each other to deliver the same kind of content to you. The race is on. They're going to share a marketplace, and they're all trying to grab a major, major revenue stream. What are some of the services that are being delivered, and how big are they? Well, first of all, these are all multi-billion-dollar industries. Ringback tones. How many in this room have spent at least 99 cents for a ringtone for your cell phone? How many people? One. And you're not the youngest person here, so that's surprising. I expected the kids to say, oh yeah, I spent, $50 on the latest jingle. I've never spent a nickel. That's a $5 billion industry. Somebody likes it. Music streaming, full song downloads, music video downloads, full video downloads, gaming, gambling, sports, every one of these multi-billion-dollar industries today. And everybody is vying for that market. That's a big game. There's lots of opportunity to think about how to deliver those services, what it means, what it's going to do to the net, what it's going to do to the edge, etc. So, but everything is not converging. There's a movement toward divergence at the same time. For example, I certainly don't want my Bluetooth earpiece to be converged with my PDA. The idea is not to do that. The idea is put this in my pocket, put it in the glove compartment, and let me talk over Bluetooth. Another thing is an implanted pacemaker. I certainly don't want that in my PDA. Okay? But I want them to talk, perhaps. Or this guy, he likes this stuff all over. He gets a kick out of being a nerd. Head-mounted displays, separate from the other device. Minority Report. Tom Cruise wants to do what he's doing there. He doesn't want that attached to the thing in his pocket. And things you didn't anticipate. You meet somebody like that on the street, and it gives a whole new meaning to the idea of transmitting a virus. Other examples of divergence. Intelligent shopping cart, intelligent room, intelligent car. Those devices are going to be distributed in the automobile. So not everything is coming into a single converged device, but there's a major, major marketplace in this convergence. So that was 4. 5, software agents. Well, the idea of putting software agents out there to do a lot of things for you, to mine the data, to figure out what's going on, to act on it, observe trends, carry out tasks, and to do adaptation. Throw out these intelligent agents, give them some kind of a goal, hopefully control them, hopefully they'll behave, neither one of which is true. That's our job, to make it work right, and get out there and do things. So what is this infrastructure vision I just described? Well, let's start with mine and earlier. Internet technology will be everywhere, always accessible, always on. We got that far. We're on our way to the next steps. Nomadic computing, it's happening. Invisibility, that's going to take a while yet. Let's expand it further now. Armies of nomads rushing about, doing their thing. Small, pervasive, smart devices ubiquitously deployed in the physical world, providing the capabilities I talked about before, all this functionality. Intelligent software agents doing their thing, basically helping to support humans. The traffic in the network will not be from humans. It will be from those intelligent agents and those smart devices. There's far more of them out there, and they have a lot more to do. Adaptive systems, self-organizing systems out there, managing a very large network. Vast, fast networks, enormous amounts of processing on vast quantities of data, hopefully making important decisions and running control systems for us. So the bottom line here, if you want to be grand and glorious about it, the internet will essentially become a pervasive global nervous system. So ordinarily I would stop right here, but I won't. Because now I'm going to ask the question you saw earlier, what the devil have we created here? You know, what's going on? What is this thing? Well, there was an elephant in the room that we're not talking about. We're creating, if you will, a vast, complex, organic system whose behavior we have no idea about. We can't predict it, and we don't know how to control it. This thing is out there. It looks like that. Did we really build that thing? It's got structure. It's got properties. It's growing. It's got its own growth patterns. We are not in control anymore. And I'm not sure you want to say it is, but something's awry here that we have to think about. How do we begin to understand these complex systems? Complexity is the issue here. That's the elephant. And we're hitting a complexity wall in many dimensions, this being one of them, where we can't make much more progress till we think about complexity as a topic in itself. It's a complexity wall, as I say. If we can't get past this, we're going to basically slow down our ability to move ahead, and it's going to make us vulnerable to all the bad things. Unforeseen behavior that we can't predict, failures, attacks, and high costs. So these are good economic reasons, social reasons, to try to think more about this, quote, monster we've created. The elephant is complexity. Here's examples of complexity in other arenas. It's all around us. These systems somehow grow. We hardly understand how they behave. We're just beginning to. We have to understand complexity. It's not easy, but we have to attack that problem. We have to be able to control it. You have three choices. You can scream at it, you can beat it over the head, or you could try to understand it and analyze and behave intelligently about it. And it's the last case, of course, we'd like to talk about. So where does it appear? Well, let's break it into a very simple case of 4 quadrants. Let's look at the question of how many parts interact versus what kinds of parts are interacting. And the easiest thing to think about is the lower left-hand corner. Just a small number of homogeneous things interacting, we can usually get an understanding of what happens there. That's not where the trouble is. Trouble comes elsewhere. If there's a small number of very complex systems interacting, each of these by itself can be terribly complex. That leads us to a certain kind of complexity. There's another kind of complexity in the lower right-hand corner, a vast number of homogeneous devices. It's the interaction and the scale which brings about behavior that is very hard to predict. And of course, in the upper right-hand corner, good luck. Okay. So we have some work cut out for us. What is complexity? Well, it's really hard to define. Okay. You can sort of characterize it by poking at it. It's a new field involving large systems of interacting parts that lies between deterministic systems and stochastic systems, somewhere on that boundary, and flipping back and forth between the two. It can refer to the fact that you can get some very deterministic behavior out of otherwise random elements, or get random behavior out of otherwise deterministic objects. Fractals is an example. So this is a rather interesting issue. What's the domain that it covers? What kinds of areas? Well, researchers come from all over the place. Hopefully you find yourself in at least one of those categories. Everybody can participate in this. They're all entering and noticing there are these issues of complexity in their own fields. These are the particular technologies that think about attacking it. There's far more you should add to that list. That's a very broad set of things to understand. So we're talking about a multidisciplinary effort here. Needs some big thinking. Networks are all over the place. The World Wide Web, the Internet, electric power grids, transportation systems, biological networks, the brain, social networks. These all have characteristics of complexity because of size and interaction. Failed networks are all over the place. From our own field, power grid failure, 2003, System 7 failure, 1990, Border Gateway Protocol, 2001, UUNet failure, 2002, Smart card system UK went down, 2005. In the early days of the internet, we had these kinds of failures. We gave them interesting names. Christmas lockup, store and forward lockup, piggyback lockup. They were there. They're still there. Not those. We found those. We fixed those. There's new ones coming all the time. What are the sources of these failures? Where does it come from? Well, let's start to think about it. Protocol errors, that's a shame. They're hard to predict. Implementation errors, they're unforgivable, but they occur. Complex protocols that interact in unforeseen ways, that's harder. We're still fighting with that one. Flow control in general causes trouble. It's necessary, and it's going to get you in the end. Random faults, cascading failures, malicious attacks. All of these things come about to attack these complex and large systems. So let's look at one example of where you can get in trouble when you think you're doing something good. Let's talk about highly structured systems. Is it a blessing or a curse? A good example is radio. Let's look at AM radio. AM radio has lousy reception everywhere. And the further you go away from the transmitter, the worse it gets. So you might simply characterize it that way. The further you go from the source, the worse the performance gets. There's a kind of constant degradation. FM radio, on the other hand, is terrific. Very good reception. Very good reception until you get to the edge, and then it fails catastrophically. Looks a lot more like that. So everybody's happy here, doing excellent, and then it crashes. Is this a good design or a bad design? Well, if you know where this point is, you might say it's a good design. If you don't know where that point is, you're in deep trouble, because it's going to fail suddenly and catastrophically when it does fail. Well, any well-designed system behaves like this. It's optimized all along the way. In fact, the more you optimize, the worse will be the catastrophe when you overload it. And you better know where the overload point is. Tends to be true for many highly structured systems. Example, congestion systems that we're familiar with. Error-correcting codes behave that way. When you go beyond the ability of the code to correct, down goes the communications. The one-horse chariot, for those of you who know what that is, was designed where everything in this horse-drawn carriage would collapse at the same time. The seat, the wheels, the horse, the straps. Perfect design. Perfect design, but a catastrophe when it occurs. So understanding complexity. We analysts thought that if we built the system, we could figure out how it works because we understand what the components are. We also recognize that natural systems are much harder. The biologists, the chemists have a much harder time because they didn't build the system. They have to figure out what it's doing. Well, no longer true. Our systems have gotten so complex that our arrogant assumption that we could manage and analyze what was going on is no longer true. It's just too complex on its own. So perhaps an approach would be to get at the macroscopic behavior. The fact is, knowing how the components behave may not allow you to figure out how the system behaves, and without knowing how the components behave, you probably can figure it out if you take the right attitude. Macroscopic thermodynamics, for example, is such an example. Okay. It's the interaction among the components, and the nature of the interaction determines the level of complexity. So we should be looking for organizing principles and not just little steps. This is just beginning. It's a wide open area. Some example networks. I'll just flash these up. You find this kind of structure in many, many systems. All of them tend to exhibit what's called a small world effect. The small world effect is that there are highly clustered sets of nodes, a small distance between any two nodes, and a kind of scale-free architectures. Some of the nodes, a few of them, are very highly connected, and most of them are very weakly connected. And you get across the network by going through the highly connected ones. The famous small world effect in social networks applies to the physical networks as well, the web, the internet, etc. So as a result, we find both resiliency and fragility in the internet. The internet has to maintain functionality under two kinds of situations. One is random failures. The other is malicious attacks by computer hackers. The good news is we can deal with the random failures. And the reason we can do that is because most of the nodes are lightly connected, and they're the vast majority. So if you knock out 30% of them, you probably haven't hit many critical nodes. So you can sustain it. Basically do the scale-free topology. Random removal is not going to hurt you. The bad news is a coordinated attacker knows where the critical nodes are. He'll take out a few of them, and down you go. What do you do? It's not clear, but the internet certainly is both fragile in this case and resilient in this case. So what do you need to do? Well, this robust yet fragile behavior is characteristic of complex systems throughout engineering. What are the laws, the underlying laws governing the dynamic behavior? And how do you match the architecture and the dynamics together? What theories, what principles, what approach can you use? Are there any common features beyond the idea of power laws that we understand so well in these networks that basically allow us to generate simple models therefore generate some general principles? Formidable challenge for all of us. Steve Hawking recently called this the century of complexity. That's where we've arrived. So, having talked about a concern, now I'm going to talk about a complaint. My complaint is with people who do performance analysis. I'm finding more and more that the papers I read and the work I see is of small consequence. People are not asking if they're attacking important problems. And when they get their solutions, they don't even understand the solution. They don't give you understanding. They give you numbers. They give you a chart. Here's a simulation. That's the performance. Thank you. Publish. Move on. There's a serious lack. I'm not talking about anybody in this room, of course. A serious lack of understanding of the things we're developing across the board. And it's embarrassing to say so. So I have 5 golden rules that I cooked up to try to talk about a little better approach to this. Here are the 5 golden rules, and I'll go through each one. Conduct a 100-year test. Don't fall in love with your model. Beware of mindless simulation. Understand your own results and look for, gee, that's funny. Let's go through these. Richard Hammond, I hope you all know who he was. Brilliant man, ornery fellow. Lots of things named after him, the Hamming code, the Hamming transform, the Hamming window. He gave a lecture in 1986 before he died called You and Your Research. And Google on that. Go find it and read it. You'll enjoy it. One of his opening thesis is, he asked the question, why do so few scientists make significant contributions and so many are forgotten in the long run? And he points out that most people, every time I met him, he would reinforce the idea you should work on an important problem, not little ones. Everybody he met told the same story. Don't waste your time on things that are not going to have some significance if you can find that flexibility. And believe it or not, most of you can, no matter how constrained you may feel you are in your own positions. He made another observation. He said, look, if you don't work on important problems, it's not likely you're going to do important work. And, you know, life is not long enough, and people can't pay you enough to do something that you don't feel is going to have some significance. So the 100-year test is the following. Hamming once asked me the following question. He said, what progress of today will be remembered 1,000 years from now? 1,000 years. That's a very interesting question. He offered an answer for one of them. He said the Hamming code will probably be remembered. And he may be right, actually. It's a kind of perfect code. But don't know. That's a good question. So let's simplify it. Let's make it 100 years. Will your work be remembered in 100 years? You don't want, make it 10 years. Make it 1 year. Pick a number. Ask the question. And if the answer is no, then it's going to make you think a little more about what you're doing. You know, you've got to at least work in areas that you think are going to have a payoff, and then do the right kind of work. So let's go to the second thing, the modeling process. Here's what modeling is. We all know there's a real world out there that needs to be analyzed. So you make a mathematical model or some other model. I'm going to focus on the mathematical model. Your next step is to solve it. Now, this is usually where a lot of us spend our time. And this is a hard job very often. Sometimes you bump into really hard problem formulations, and it's hard to get the solution. So one thing you can do is make an approximation right there. Don't give me an exact result. Give me an approximate result. All right, that's one thing you can do. But you can beat yourself on the head, you know, for months trying to make that step and blame yourself if you can't get there. My advice to you is don't fall in love with your model. Because this model does not represent the real world exactly. You made some approximations right there. So why not go back and make a different model? Choose a slightly different model that may allow this step to be far more simple and may give a better result here than if you took the original model and came up with an approximate result or no result. There's 2 places to make the approximation. It's very important. And when you're all done, of course, you got to come back and check. Does it really match the real world? A lot of people fail to make that step. A lot of people are unaware you can do this step, and they beat themselves here. Okay. Don't fall in love with the mathematical model. Maybe it get you out of a box if you're in those box now. Let's look at simulation. You see these curves all over the place. Now beware of mindless simulation. People present a curve and say, there, see, that's how it works. And then you go on. Yeah. Well, what is it telling me? You know, it told me how that particular system worked. There's some obvious things to look at when you see a picture like this. One of them is to ask the audience, gee, it looks like something's going on there. There's a kind of linear behavior there. Maybe there's a deterministic or simple model that explains that. And if so, what are the parameters of that model? For example, what's the slope of that line? How is that slope of the line related to the underlying system parameters? And what's that intercept? Little things like that. Please give me that. It's asking to be found. And of course, there's more in that picture. There's an asymptote. What's causing the asymptote? What's saturating? How big is it? Give it me in terms of kind of some general variables. Don't tell me it's 3.6. Tell me it's when the system capacity is maximized or limited or something. And of course, give me that value. And the third thing is, there's something really interesting happening at that point. First of all, what is the value there, algebraically? And then next, what's the meaning of that point? And there's something on this x-axis which changed dramatically the performance right there. If you give me those numbers even in a more approximate model, I've learned something more generally, perhaps. It's not a perfect representation of this case, but it may allow me to enlarge my thinking about many other cases. So beware of mindless simulation. Let's go on. Understand your own results. You know, what are these results trying to tell me? The best time I spend with my graduate students is sit down, look at a result and say, okay, now what is it trying to tell us? What does it mean? You know, why? Tell me something. Don't just give me, you know, even an equation may not explain it. I want to know what's the physics. Why did this happen? And from there you get some better results. Let's look at an example. I'll show you one very old example. Here's a network. There's an input. There's a capacity limitation. There's some throughput. There may be some loss. And there's a response time. So let's look at a couple of those parameters. Let's look at a famous response time versus throughput curve. It usually looks like that. So let's ask some questions about a curve like this. Let's ask a good question, for example. Do you want to operate there? Terrific throughput, lousy response time. Or do you want to operate there? Lousy throughput, terrific response time. What's the answer? Well, it's not obvious from this. So let me define a new metric of performance. The metric is going to be the ratio of throughput to response time. Let's just throw it out there. Doesn't mean anything. You want it to be big. You want a lot of throughput and a small response time. Okay? So let's look at that. Mathematically, that's what it looks like. If you look at that point, there's a power associated with that point. It's 1 over the slope of a line out of the origin. Okay, that's sort of interesting. If you want to maximize the power, assuming that's the new metric you're after, turns out to be that's the condition. When that's true, you've maximized power. It's a necessary condition. That's published in that paper many years ago. Understand it. Is there some physics here? Well, let's see. It's telling me that the first point of tangency out of the origin is where the maximum occurs. That follows immediately from the definition of 1 over power right here. Okay. Can I learn something from that? Well, I'd like to understand that result. By the way, the result applies no matter how complex that curve is. The first point of tangent, it can be discontinuous. It's the lowest point. The line out of the origin, the smallest slope will maximize the power. That's interesting. Well, okay. Let's go a little further. Let's dig deeper. Let's look at that and say, gee, something is going on there. In the case of MM1, that point occurs at rho equals a half, namely when the average number in system is exactly 1. Well, that's sort of interesting. Is there a way I can explain why that's happening? Well, let's go to a very simple model. Let's look at a queue. People arrive to get served. Others wait in the queue. Let's assume I can keep some people out of the queue by some control mechanism. Somebody leaves. And suppose I want to measure the response time in that light green box, light blue box, whatever the color is. And suppose I ask you to minimize, structure the system to minimize the response time in this box. At the same time, please maximize the efficiency of the server. There's a pretty obvious way how to do that. Allow only one person in there at a time. Serve that person, keep the server busy all the time. When that person leaves, put one more in. Nobody ever waits inside the box. They're only being served, and the server's always busy. Perfect. So the intuition is just keep the pipe full. Well, our earlier result, the intuition says, put exactly one person in the system. That's a deterministic result, if you will. But you can't do that in general. You can't really control a queue that way. Our earlier result said, on average, put one person there. The intuition says, if you can, keep exactly one person there. When there's less than one person, you lose some efficiency. When there's more than one person, you're eating up a little bit of waiting time, a little bit of response time. But that's what it's telling me. So now I think I understand a little more why that result turned out that way. But gee, that's a little funny. And this is the fifth principle. When you see something that's sort of funny, poke at it. Poke further to see if there's more. What can we say for MG1 if that's true for MM1? Well, that's the solution for MM1. MG1 is going to have exactly the same behavior. This line, this locus of optimal points, you'll find, has exactly the same property. On average, there's one person in the system at that point. Now you've learned something more. You've generalized by looking at that characteristic, not looking, for example, at some very complicated value of rho, which is a horrible expression, but a very simple invariant in this case. Well, I'm not saying this result is all that important. I'm saying poke around at the result, keep thinking about it, see if there's more there, and try to understand what's going on. So a few more comments on modeling. Moving the frontier is hard. You all know that because you've moved it. But we cheat our students when they come to our classes, and we show them all the beautiful results that are out there in the literature. Oh, look at this, look at that performance. Boy, that system solved like that. And they think it's easy. Then they start doing research, and they can't move the frontier a micro-inch, and they think they're failures. Because you haven't told them it really was hard in those early days. Well, in fact, in today's day, when you had to move the frontier. So you don't want to mislead them. You have to warn them that you've been cheating them in class. The world is not as well crystallized as you pretend to be. Secondly, once you get past your first result, you can probably do more. Because students usually get discouraged along the way. They're there for 6 months, a year and a half, and they get nowhere. Tell them to stick to it. Once they get one result, it'll give them the confidence that they can move ahead. In fact, it's a highly nonlinear process. Highly nonlinear. I know when a student's ready to graduate. You know, I present them with something to work on. They come back 2 weeks later, and they've got no results. Give them another idea. They come back. One day they come back, and they race ahead of me. I know then they're ready to graduate. Okay? They become experts in their own field. But until that day, they don't believe it. You know it, but they don't. Third, as I said before, sit down with them and make sure they and you understand what they've done. Not just present an equation or a set of numbers, but the meaning, the interpretation. Why is that happening? And of course, generalization usually comes when you see the simplicity of a solution, not the complexity, the simplicity of it. Then you can make a leap ahead. And the last is, if you want to be successful and stay interested, try to be aware of fields around you that have the opportunity for some more interesting things to happen. Don't stick in one place always. There's related fields that are more virgin than the one you've been mining for 5 or 10 years, and the rest of your crew has been mining. So look for other opportunities. So, in conclusion then, I'd say we've come a long way. Or have we? And that's especially interesting if you're interested in queuing, but there's many meanings to that picture. So thank you very much. Are we going to take questions now? Harvey? Jody? Charlie?
Recently there's been, I can just shout.
Louder.
So there's been recently discussion about a multi-tiered or multi-dimensional internet by which I think has meant that you can charge more for higher quality. Oh, thank you. So the idea has been raised of a multi-dimensional or multi-tiered internet so that you could charge more and get better service. Some people say this is great because it can really enable much more interactive internet. Some people say it's terrible because it might cause the internet to no longer be democratic. I wonder if you have any comments about this.
So you're asking one of these social questions now, and it's an important one, I agree. Part of the response relates to what we call the digital divide, which already exists without this tiered service, and that's bad enough. This is likely to let the rich get richer and the poor get poorer. On the other hand, there may be some critical applications that need this kind of service, and depending upon the importance in terms of the social good, you know, to send the latest movie out of Hollywood at the most expensive rate may not be the most important thing, but perhaps to send some information about a disaster or an emergency might be. So I can see both sides of the argument. I wouldn't basically say it's black and white. There are times when it could be useful. I would not like to see this as a general situation. This reminds you of the paper I wrote on optimum bribing for Q position. That's what this is. This is bribing, to give it a nasty tone.
Is there any other question? Okay, then we go to the coffee break and recombine here at 11:30. Thank you very much. Thank you, Leonard.